Okay, this is our lab setup for this week. It's not quite 100% set up yet, but I want to walk you through the parts. Um, this here is a cathode ray tube. It's part of what you might have had in the back of a really old TV. An old CRT stands for cathode ray tube. And those kind of televisions used a beam of charged particles to display an image. So we don't have quite that fancy of one today, but it's equipped to let us make some measurements about those charged particles. These things here are called Helmholtz coils, and they're going to allow us to produce a magnetic field at any strength we want. Over here we have our power supplies. This one is a high voltage power supply. It can provide up to 5,000 volts. And this here is a quad power supply with different sources depending on what we want to use it for. And so we're going to use two of these today. The leftmost one is a 0 to 500 volt supply, and the rightmost one is a 0 to 12 volt power supply. What good is a lower voltage? Well, it can provide a much higher current. So this can provide 12 volts at 4 amps, which is about 48 watts of power, whereas this can provide 500 volts, but only at 50 milliamps, which is quite a bit less power. And so we're going to need a lot of power to produce a magnetic field, but not so much power to produce the deflection, which is what we're going to use the higher voltage for. Let's look at the circuit diagram for this thing. In the back of the tube, we've got what's basically a parallel plate capacitor. And the positive plate of that capacitor is in the front. That has the higher potential, and the potential difference or the voltage between those two plates is called delta V accelerating, and that's what we apply with the high voltage source, the 1,000 or 2,000 or 3,000 volts. After that charge gets ripped off that glowing filament, it flies towards the positive plate. That tells you something about what kind of charge it is, positive or negative. And then it flies through a second parallel plate capacitor. In this case, the positive plate is on the top, the negative plate is on the bottom, and the potential difference or voltage between those two plates is called delta V deflection, delta V DEFL. And that whole setup, the whole parallel plate setup on the side is surrounded with coils that carry current, and that current goes around clockwise and produces a magnetic field that goes to the diagram, represented by those circled X's. Okay, so first things first, I have the lights off. I'm using my phone flashlight to give us some light here. And what I'm going to do is I'm going to turn on the high voltage power supply, but have it set to 0 volts first of all. We're going to see what happens. Okay, so I just clicked it on, and you notice the first thing that happened is right over here, we've got some glow happening. And you can see the remnants of that glow leaking out through a slot on the front, but that's not anything, that's just some light reflecting. So what we're going to do now is I'm going to slowly crank up the high voltage knob. And now you can see I can completely turn the phone flashlight off. You can see a blue line. And I'm cranking that up now, and the higher I crank that line, the more intense that blue glow gets. And so what's happening there is my high voltage supply is accelerating charged particles off of that hot glowing filament in the back. So it's glowing like a light bulb in the back end, and I'm applying a very strong electric field, and that's ripping the charged particles off and sending them at high speed through the rest of the tube. Okay, now I'm going to apply a magnetic field. I've got a bar magnet here with labeled north and south poles, and I'm going to make it so that the north pole is heading into the screen here, is heading into the direction of the beam. So the magnetic field lines are coming out of the front of that magnet there, and I'm going to direct them over to the beam of charged particles and see what happens. And just to check, here's the south pole. So notice that the charges are neither moving towards nor away from the magnet, but they are moving perpendicular. They're being deflected perpendicular to both their velocity and to the direction of the magnetic field. Alright, now I'm about to apply a voltage between the plates, and this here is set up as a parallel plate capacitor. The bottom plate is going to be at the negative plate. It's at 0 volts, and the top plate is going to be our positive plate, and it's going to be at some voltage that we get to pick. We get to dial it in with this knob. And so turning that on, right now I'm setting it to about 100 volts, and you see there's an upward deflection there. Let me crank it up. 200 volts on that top plate. There's 300 volts, and dialing it back down to 0. And we're back at no deflection. Okay, so now I've got these coils, these Helmholtz coils, into the circuit. So I've got the 12 volt supply powering these, but it's adjustable, so it can be between 0 and 12 volts. And I've got from the positive terminal, it's going through an ammeter here, so I have this set to the 20 amp limit. We're not going to actually have more than 1 amp going through it. It's coming out and it's going around the first coil in this direction, out this wire, back to the back coil, and then going around in this direction. And using the right-hand rule for currents, we have our currents going this way. That means the magnetic field is curling around them this way. So I've got a magnetic field going this direction, just like the magnetic field we applied with the north pole of the magnet, like this. So I can apply the north pole and get this deflection, or I can crank up the current in this magnetic field and get quite a bit stronger deflection. It's very easy to make a strong magnetic field with current, quite a bit stronger than a bar magnet. So this is the max that I've got. I'm at 0.96 amps, and I've got this nice strong deflection. And you notice that those charged particles are moving more or less in a circle. They're curving in roughly uniform circular motion. Now I can turn the magnetic field back down to 0. So what we're going to do now is we're going to take some data, and the data that we're going to take is measurements of all 3 of our values at once. We're going to measure the accelerating voltage. Right now I have it set to 2.5 kilovolts. I have the deflection voltage turned off, and I have the magnetic field current turned off. But what we're going to do is we're going to turn on the deflection. So I'm going to turn that electric deflection up to, let's say, 100 volts. I'm going to put it as close as I can to 100. That's very close to 100 volts of deflection. And then I'm going to adjust the current, so I'm turning up the current now until I get the trajectory as straight as possible. And there's no way to get it perfectly straight, because the electric field isn't perfectly uniform and the magnetic field isn't perfectly uniform, but they're both close. And so we can get it as straight as possible, sort of on an average over the whole line. So that to me looks about as straight as possible. So I'm going to record the data, 2.5 kilovolts for the delta V accelerating. I'm going to record 100 volts for the delta V deflection, and I'm going to record 0.14 amps for the magnetic field current. From that, I'll have to calculate the electric field and the magnetic field and the speed of the particles. And with several more data points, I can work out the relationship between the charge and the mass of these moving particles.